about waves in one dimension and two dimensions is they have pretty much the same qualities, I would say. But what we will see at that is called as the waves in two dimensions are things or the way that the wave behave when it reaches a barrier. And this barrier can be a horizontal surface in which the wave just hit the surface and then is reflected, or it can be a barrier that the wave goes around the surface or through a opening on the surface. So if the wave is moving on the same medium after it is hitting the surface, it is known as the reflection. So when the wave, it hits the surface and then it is reflected from the surface on the same medium. So this is same medium. The phenomena or what is happening with the wave is known as the reflection. The reflection is managed by that is known as the law of reflection. And the law of reflection is saying that the angle of incident is equal to the angle of reflection. But what is the angle of incident? So if we represent the wave with just the direction in which the wave is moving, and this will be this one here, perpendicular to the surface, we draw a line, and then the angle that is created between the perpendicular to the surface and the incident wave is known as the angle of incident. And as it is reflected, then the angle that is created between the reflected wave, direction of the wave, and the perpendicular to the surface is known as the reflected angle. And the law of reflection is stating that the incident angle is equal to the reflected angle. Now you may ask, why are we doing the normal perpendicular to the surface? Because in math and in physics, in the world of physics, every surface is identified by a vector. And then this vector that identifies the surface is perpendicular to the surface. So actually this is, you will learn it when you go to a higher level, is the vector that represents this surface here. This is why we take the angle with the perpendicular to the surface and not the angle with the surface. Okay, is it clear? Let's figure out now what is happening with the wave that is traveling and it is hitting surface A. But surface A and surface B create between each other a 180-degree angle. So what is happening with a wave? What is the way that wave will travel on this case? So the wave is incident in boundary A, in surface A, and reflected to boundary B. What is the angle of reflection at boundary B? So as the wave is traveling, it is hitting surface A and it is traveling on the same medium. And then based on the angle of reflection, what we will see is the angle of incident is equal to the angle of reflection. So this is what will happen when wave is hitting surface B. And since the angle of incident is equal to the angle of reflection, and we know that the angle of incident is 50 degrees, we can say that the angle of reflection is 50 degrees as well. So this angle here is 50 degrees. Okay. Now, perpendicular to surface B, we will have this line here, the yellow dotted one. And then again, we are traveling on the same medium. What is happening, the wave will travel in this direction. And what we have here is the new incident angle of the wave is equal to the new reflected angle of the wave. So those two angles are equal to each other. However, what is this angle? We can find it using two principles of math. The first one is complementary angle. So we can find this angle alpha here as alpha plus 50 is equal to 90 degrees. Those are complementary angle. And from here, angle alpha will be equals to 40 degrees. And then it is found based on the fact that the sum of inside angles in a triangle is 180 degrees. So then we will have this angle alpha plus 110 degrees plus angle beta here equals to 180 degrees. From here, we can say that angle beta is equal to, since this is 40 degrees from the previous step that we did, then this will be equals to 40, am I right? 40 degrees, am I right? I was not right. This is 30 degrees because 180 minus 150 is 30 degrees. So angle beta is 30 degrees. Now, what is the angle, the new angle of incident for the wave as it is hitting surface B will be again using the complementary angle, that angle of incident plus angle beta is equal to 90 degrees. From here, angle of incident will be equals to 90 minus 30 degrees equals to 60 degrees. So this angle here is equal to 60 degrees. Based on the law of reflection, that the angle of incident is equal to the angle of reflection, then we can say that angle of reflection is equal to 60 degrees as well. Is this clear? The second phenomena that we notice when we have a wave that is traveling is that is known as the refraction. Refraction is happening when you move from one medium to the other. So let's say that we have moving from air to water, from water to diamond. So when it is moving from one medium to the other, what do we see is the reflection. And now I will draw a picture of a refraction situation, sorry, a refraction. So as it is moving from one medium to the other. So you have here a surface. And then here you have medium 1. And here you have medium 2. So this surface has that normal that is perpendicular to the surface, and we said why is it like this? And then you have an incident ray that comes on this direction. So incident ray or wave that comes on this direction, creating an angle with the normal. Okay, this is known as theta 1, which is the incident angle. As is it moving from medium 1 to medium 2, this angle changes. So this will be the refracted ray or wave ray. Okay, creating an angle of theta 2, which is known as the refracted angle. Okay, so now what is it saying here based on that is known as the Snell's law? It is saying that the ratio between sine theta 1 and the sine theta 2, sine theta 1 is the same as the wavelength 1, so wavelength of the wave on medium 1 over wavelength on wave on medium 2, and speed on medium 1 and speed on medium 2. You have this in your formula sheet with probably N2 over N1, something like this. Can you please check? Now, you may say, Miss, what is happening? Is it reflected again? Yes, it is. Yes, it is. So this wave is reflected as well. And then we have here the angle of reflection, which is following the rule, the law of reflection, saying that those two angles are equal to each other. But the angle theta 1 and angle theta 2 will follow the Snell's law relation. Sine theta 1 over sine theta 2 is equal to wavelength 1 over wavelength 2, or speed 1 over speed 2. Now you can see here that if theta 2, which is the angle on medium 2, is less than theta 2 is less than theta 1, then we can say that it is traveling slower on medium 2. Than in medium 1. Okay, so let's take a look at this example that we have here. Water wave traveling in a deep water at 15 meters per second enter a shallow region with an angle of incident of 30 degrees. The angle of reflection is 22. What is the speed of the wave on this shallow region? And we will see even here what we said in terms of the velocity. Okay, so now we will take Snell's law saying sine theta 1 over sine theta 2 is equal to V1 over V2. We don't deal with the wavelength on this case because they're not asking, they're not giving us any information. So now we have sine 30 degrees over sine 20 degrees is equal to 15 meters per second over V2. From here, we can find that V2 is equal to 15 times sine 20 over sine 30. Use your calculator and tell me. So this should be 22, not 20. Then V2 is, I have here 11.2 meters per second. So as I said, like if the angle in this one of the mediums is smaller than the angle on the other medium, then we can say that the wave is traveling slower than on the other one. Do you have any questions? A wave travels from a region with a speed of 45 meters per second into a region with a speed of 60 meters per second. If we were going to draw this particular situation, this is the surface and this is the perpendicular. So now it is going from a lower speed to a higher speed. So you will have to draw something like this. This is the incident and this is the reflected. So the speed on medium 1 is less than the speed on medium 2. This is theta 1 and this is theta 2. But we will see even from here what it is. So now we have V1 as 45 meters per second, V2 as 60 meters per second. In the slow region, so lambda 1 is equal to 1.5 meters and lambda 2 is question mark. So we'll use the Snell's law, which is saying V1 over V2 is equal to lambda 1 over lambda 2. Okay, we will omit the sign part here because no information is given and they are not asking us for anything. So then we'll have 45 meters per second over 60 meters per second is equal to 1.5 meters over lambda 2. From here, lambda 2 will be 60 times 1.5 meters, because meters per second and meters per second cancel out, over 45. So lambda will be in your calculator, will be 2.0 meters. Is this clear? Diffraction, it is happening when you go around the corner or when you go into an opening, okay? So what is happening here when you go around the corner as the wave is moving on this direction and then it hits this corner here, then it's kind of hugging the corner. So this phenomena is known as a diffraction. And even when you have that the wave traveling on this direction and you see a small opening, then what is happening is the wave is kind of creating a new wave front because each particle of the wave is acting as a wave on its own, and then it is creating this ripple here. This phenomenon is known as the diffraction. Interference, on the other hand, it is when they are interfering between them, when they are meeting each other at a certain point. So interference can be constructive and deconstructive, fully constructive and fully deconstructive. Let's suppose that we have a wave S1 that is moving on this direction and wave S2 that is moving on this direction. They meet each other at a certain point. This is the point where they meet. Now, if they are meeting each other at the same phase, meaning that they are either both at the lowest point or at the highest point or at any point that have the same direction, then this is known as the constructive interference. What is happening? You will see a wave that is with a highest amplitude. But when they meet, that they are not in phase with each other, like in this case here, wave 1 is moving on this direction, wave 2 is moving on this direction. Here is where they meet. This is the meeting point. Then what is happening, they are meeting each other out of phase. So when the maximum of the first one is reached, the minimum of the second one is reached. Okay, and then as they meet each other, they cancel out each other. So this is known as the total deconstructive interference. So points S1 and S2 are sources of the two identical waves. You can say two identical waves or not. It doesn't really matter. The constructive and deconstructive interference happens even when they are not two identical waves. But when they are two identical waves, what we see in the constructive interference, we see an amplitude that is double. And what we see in a deconstructive interference is that the two amplitudes are canceled out and there is no waves after the two waves are met. If they are not identical waves, what will happen in the constructive interference, the wave that is created is with an amplitude of the sum of two amplitudes. And what is happening on the deconstructive interference when you don't have two identical waves is that the wave will be with a smaller amplitude. So the largest amplitude minus the smallest amplitude will be what you will see in a deconstructive interference. Now, since we have two identical waves, that means that we have two waves that have the same characteristics, the same amplitude, the same frequency, the same wavelength. Now we have 2 point sources, S1 and S2. Those are, in this case, is a water wave, and they meet each other at point P. PS1 is 80 centimeters and PS2 is 90 centimeters. Explain whether will be a constructive or deconstructive interference between the two waves on the case when the wavelength is 5 centimeters and wavelength is 20 centimeters. So now keep in mind, the distance between P and S1 is 80 centimeters and P and S2 is 20 centimeters. So in the first case, when the wavelength is 5 centimeters, what do you see is if you divide the distance between PS1 and 5, you will see that you will have 16. That number means that you will have the wave 16 times here, okay? And when you divide the distance by the speed, now the wavelength, sorry, 5 centimeters, then means that you will see this 18 times going for the wave 2 or source 2. You will go 18 times. So when they meet at point P, what is happening, they are on phase with each other. So they are both, let's say, at the highest point or both at the lowest point. So since the difference between 18 and 16, how many times do you see the wave meeting at point P is a whole number, then what is happening is a constructive interference. Let's do the same calculations for the case that the wavelength is 20 centimeters. So if you see here S1 and S2, and point P being here, again, 80 centimeters and 90 centimeters. So what do you see for the first one is it's completing 4 complete circles, okay, when it is moving from the source to the point that they meet. And for the second wave, it is meeting 4.5, so it will have a half circle completed, and then we'll have 4 more, okay, when they're meeting here at this point. The difference between those two is a half wavelength or half point. That means that what will happen is a deconstructive interference. So what you will do is you will see how many times you have from one source and how many waves or cycles you have on the second one, and then make the difference. If it is a whole number, then it's a constructive interference. If it is 0.5, then it is a fully deconstructive interference.